So good morning everyone. Today we're going to see about the graphical processing unit virtualization. So imagine you and your friends are going to a restaurant and only one powerful chef was there. So instead of cooking for just one person, the chef prepares multiple dishes simultaneously for different tables. So now think, what if a single powerful GPU could serve multiple users at the same time? That's exactly what we call GPU virtualization. So let's understand the real world problem that in today's world, AI training needs massive GPU power, gaming platforms requires high performance graphics, hospital process MRI scans using GPUs. So but there is a issue, GPU are very expensive. Many times GPUs stay idle. Users cannot easily access them remotely. So when it comes to the needs that high performance parallel processing, cost effective access, multiple user support, efficient resource sharing. So let's consider a real time analogy that you think of a college bus. Instead of one student using one bus, many students share the same bus. Similarly, many users share one GPU. So where do we actually use GPU virtualization? AI and machine learning, virtual desktop infrastructure, cloud gaming, medical imaging, all those things we use the GPU virtualization. For example, think about Netflix streaming. Okay, you don't own a movie, you stream it from a server. Same way, GPU power is streamed remotely. For example, a gamer plays a high-end game without owning a GPU. A doctor analyzes scan faster using shared GPU power. So now what's the problem do we face without using GPU? If we don't use virtual GPU, what all the problem it will cost? So the first problem is high cost. So we need to buy multiple virtual GPU. And then underutilization. Most of the time the GPU is idle, it is not used. And then limited access and complex management. For example, to make it understand easily, let us consider you are buying a luxury car but using it only once a week. So here the waste of money and resources. Like this, the GPU is purchased and if it is idle, it is waste. So GPU virtualization solves this. Let's define it clearly. GPU virtualization means dividing a single physical GPU into multiple virtual GPUs. For example, one GPU is equal to multiple virtual instances. Multiple users simultaneously access the GPU. So there is a dynamic resource allocation. For easy understanding, let's consider pizza. Okay, the think of a pizza. There is one pizza is divided into slice. So each person get a slice. Like this, GPU is like the pizza. User gets slice. Now let us understand different methods. So there are two methods to use this type of GPU virtualization: pass-through, create pass-through, GPU emulation, and API or remote. So when it comes to pass-through, one GPU is equal to one virtual machine. So it is high performance. Immediate pass-through, it is that GPU shared among multiple virtual machine. And GPU emulation is nothing but virtual GPU creates by a software. API remoting is that command send remotely. To make it understand these four types easily, let's consider the mobile hotspot sharing. One person shares internet, others connect to and use. Different sharing methods, different GPU virtualization types. The two major industry solutions nowadays are hardware-based virtualization, multiple profiles, enterprise-level virtualization. So here,
So the report really boils it down to three main ways to do this. First up is pass-through. Think of this as the simplest approach. You give one entire physical GPU to one single virtual machine. It's all about raw, unfiltered performance. Then you've got vGPU. This is where software cleverly divides a GPU's processing time among a bunch of different users. It's perfect for maximizing density, getting more people on a single piece of hardware. And finally, there's MIG, or multi-instance GPU. This one's a game changer because it actually partitions the GPU hardware itself into truly isolated, secure slices with guaranteed performance. So what's the catch with each of these? Well, it really all boils down to performance trade-offs, and this chart from the report shows it perfectly for an AI training workload. At the top, you've got bare metal. That's your 100% baseline. Now look at GPU pass-through. It's right up there at 97%. That's incredible. A MIG instance is also really solid, giving you a guaranteed 90%. But then you get to vGPU, and you see the trade-off. In a low-density setup, you're still doing pretty good. But as you cram more and more users onto that GPU, high density, you see a real performance hit. This right here is the central decision you always have to make. Do you need raw power, or do you need user density?